So we would like to compute the surface area of the sphere of radius r, and we might as well consider it centered at the origin. And we would like to use a scalar surface integral in order to compute that. In general, when we wish to compute surface area, we just need to compute the scalar surface integral of the function 1 on this surface. Let's call it S. And what will be interesting in this case is that we will use a very unusual parameterization. Let's recall in general that a scalar surface integral of a function f along a surface S is given by a usual double integral over the domain of a parameterization. Let's call it g of uv times the magnitude of the normal vector which is attached to this parameterization. So this is the formula that we wish to implement. The nice thing for us here is that the function f is the function 1. No matter how you compose it, you still get the function 1. So what we really need to compute is the normal vector, and that's what we're going to do. But first of all, let's explain what kind of parameterization we're going to get to use here. So instead of using u and v, I'm going to use the more suggestive letter variables theta and phi, because we will see that our parameterization will be inspired or heavily depend on knowledge of spherical coordinates. In particular, the parameterization will be the following. So r sine phi cosine theta, r sine phi sine theta, and r cosine phi. And here phi is, or theta is going to run from 0 to 2 pi, and phi is going to run from 0 to pi. And let's explain what we're doing here. So if you temporarily replace r by rho, then what you're looking at in these three components are simply the expressions of x, or I should include everything here, x, y, and z. Right? So these are the expressions of x, y, and z with respect to spherical coordinates. And if we actually replace rho by r, meaning we fix r, then we restrict to the surface of the sphere of, or to the sphere of radius r. And by allowing theta to run from 0 to 2 pi, strictly speaking, we just need to go all the way to 2 pi without including 2 pi, and phi to go from 0 to pi, we pretty much traverse the whole sphere. So this is a parameterization of the sphere. Now, let me erase those things so that we can continue here. And the next thing is to find the normal vector. And we know that for that, we need to take the cross product of the two partial derivatives. When I say partial derivatives here, we have a vector valued function. So what we mean is to take the derivative of each component with respect to the corresponding variable. So what is g sub theta? So we will have r sine phi, and the derivative with respect to theta is negative sine theta. So I'm going to put negative sine theta for cosine theta. And then we're going to have r sine phi cosine theta. And then I'm going to put 0 because the last component doesn't have any explicit occurrence of theta. And we're going to cross this with the partial derivative with respect to phi. So here we will have our cosine phi cosine theta, our cosine phi sine theta, and negative r sine phi. Now, before we take the cross product, it might be a good idea to factor out as much as we can. And what we can factor out is an r from the first vector, also an r from the second vector, so an r square altogether, and the sine phi from also the first vector. So what we need to take the cross product of is simply minus sine theta cosine theta 0 cross with cosine phi cosine theta cosine phi sine theta, and then minus sine phi. Okay, so let's take this cross product in a traditional way. So we will have I, j, k, and then let's write the components. So minus sine theta, cosine theta, 0, and then cosine phi, cosine theta, cosine phi, sine theta, and negative sine phi. Okay, so let's compute this determinant. So what are we getting? It's a vector, of course, we're going to get. Start by deleting the first row and the first column in order to see what will go on the first coordinate. So that is going to be a negative cosine theta sine phi. Now delete the first row and the second column in order to see what will go in the second coordinate. So that turns out to be sine theta sine phi, but there's an extra negative, so that will be minus sine theta sine phi. And finally delete the first row and the last column. And what we're going to get is, let's try to write it in detail, minus sine square of theta cosine phi minus cosine square of theta times cosine phi. So you can see here that if you factor out a negative cosine phi, then you get sine square of theta plus cosine square of theta, which is simply 1. So the whole thing is negative cosine phi. So what we have is r squared sine phi minus cosine theta sine phi minus sine theta sine phi and minus cosine phi. And what we really want to do here is take the normal vector, the magnitude of this normal vector, which is going to be the constant that we have, or the factor that we have in front. Notice that phi is between 0 and pi, which means that sine phi is non-negative, so we can leave it without an absolute value, and then we need to take the magnitude of negative cosine theta sine phi minus sine theta sine phi and minus cosine phi. And you might think that this is a bit of a mess, but do you see what is going to happen here? I mean, this is very reminiscent of computing the Jacobian for spherical coordinates, and this is certainly not a coincidence. So this is going to be r squared sine phi times the square root of cosine square of theta sine square of phi plus sine square of theta sine square of phi plus cosine square of phi. All the negative signs disappear. And what you have from here is really, if you factor out sine square of phi, you will have cosine square of theta plus sine square of theta, which is 1. So the whole thing is sine square of phi. So when you combine it with cosine square of phi, guess what? It gives you 1. So we simply get r squared sine phi. So that's the absolute value or the magnitude of our normal vector. And remember, if we go back to our formula, we just need to integrate this over the domain of the parameterization. So eventually, the final answer will be the integral from 0 to 2 pi matched with d theta, integral from 0 to pi matched with d phi, and we're integrating r squared times sine phi. There is no theta, so we have a multiplication with the length of the interval of the integration with respect to theta. R squared is also a constant for this integration, and eventually we'll land with the integral from 0 to pi of sine phi d phi, the antiderivative here being negative cosine phi going from 0 to pi. And this is negative 1 minus negative 1. So it's actually 2, giving a 4 pi r squared. And what is interesting here to notice is that, do you remember what the volume was? We computed that before of the ball. The volume of the ball was 4 pi r cubed divided by 3. Now, if you take the derivative of this with respect to r, guess what you get? Exactly 4 pi r squared, which is the quantity that we just found. If you think this is a coincidence, then consider the two-dimensional situation. So the formula for the area of the disk is pi r squared. If you take its derivative with respect to r, what do you find? 2 pi r, which is the circumference, the length of the circumference of the circle. None of this is a coincidence, and we could put this in a much more formal perspective, but we will leave it at that with this little remark just to juice things up and to possibly stimulate your curiosity. And that's all there is to it for this nice little computation of the surface area. Thanks for watching.